All right, so before we do this last example, um, let's talk about this box that defines a new term called an inflection point. Okay, so this is good vocabulary to know. Um, and essentially what you need to know is that an inflection point is just a place where a function changes concavity. So if a function is continuous at a point P and f changes concavity at that point P, either from concave up to concave down or concave down to concave up, either way, that change in concavity, that point where a change of concavity occurs, is called an inflection point. Okay. Of course, it has to be continuous at that point for it to be a inflection point. So you could have, for example, you could have a function change concavity at an asymptote, like a vertical asymptote. That wouldn't necessarily be called an inflection point because it's not continuous at that inflection point, right? There's if there's an asymptote, right? So here, let me kind of draw what I mean, right? So like if you had a function where there's like a vertical asymptote, and let's say your function goes like this, it's concave up, and then maybe it switches to concave down, right? Now that point at that asymptote, it changes concavity, but that point is not part of the domain, right? This point, if we called this P, this is not part of the domain. So in this case, P is not an inflection point. Okay, so this definition only holds for a continuous function. So like if you go back and look at this example up here, you can see that this point right here at A, where it changes concavity, that would be an inflection point, right? It's continuous at that point, and it changes from concave up to concave down. So that would be an inflection point. Inflection. Point. Okay. Sloppy writing, but that's okay. All right. Inflection point. All right, so inflection points. All right, now you're probably going to see in the online homework a lot of problems like these. So I want to go over at least one example with you. Now it says, first of all, says use the first derivative to find the intervals on which f is increasing and the intervals on which f is decreasing. Okay, so remember, we can tell if a function is increasing or decreasing based on the first derivative, right? So we want to look at the first derivative and then find where the first derivative is positive and where it's negative. All right, so let's first of all find the first derivative. All right, so we're going to have 3x squared minus 12. All right. Now, this could be positive and this could be negative, right? Or it could be negative. So the places where it changes concavity, or the places where it changes from positive to negative or negative to positive, as long as it's a continuous function, it's got to pass through 0, right? And so what I'm going to do here is set this equal to 0 and find the places where it might be changing from positive to negative. And then I'm going to evaluate that. So if I set this equal to 0, you can see, all right, let's factor out a 3, and then we're going to have x squared minus 4 equals 0. And then I'm going to factor this. I'm going to have x plus 2 and x minus 2. Okay. All right, so I factored it. Now, if you had like added 12 to both sides, divide by 3, and then take the square root, you just can't forget about that there's a positive and a negative solution, right? So this thing is equal to 0 when x is equal to negative 2 and 2. All right, so let's divide our domain at those points and see what's happening on either side of the function, or sorry, either side of those points. Okay, these are sometimes called critical points. We're going to get into more of that later, but these are often called critical points. All right, so one thing you might do is just, you can even draw a number line. You can even draw a number line and mark the critical points on there. And 2. All right, -2 and 2. And then pick a point in each part of the domain, right? Imagine this is the x-axis, and so we want to pick a point that's less than -2. So maybe we evaluate f prime at, say, -3, right? And again, I kind of like to use the factored form. It's 3 times -3 plus 2 times -3 minus 2. Now, I'm only trying to figure out, is the derivative positive or negative on that interval? So I just picked a test point. So I don't really even care about what this number is, right? All I know is it's 3 times a negative number times a negative number, right? I could calculate that. But what I'm going to get is something positive. Okay. So some of these, this one's not too hard to, this one's not too hard to evaluate, but sometimes, especially if you don't have a calculator, all you really need to know is the sign. So this is negative, negative times negative is positive. And so this value is greater than 0, right? Greater than 0, which means it's increasing. So sometimes you can just draw, it's increasing. So I'm going to draw a little arrow on my number line. So it's increasing in that interval for x less than -2. So increasing, I'll just write this down. We're increasing on x less than -2, or you could use interval notation and use -infinity to 2. Okay, so it's increasing on that interval. Now, I'm running out of room here. Maybe I'll move this. Sorry about that. I bet you hate when I do that. I move this stuff around and then you're trying to take notes, right? So I'm just going to move it so I have some more room to do some more calculations, because I need to look at now a number between 2 and -2. So I think an easy thing to choose would be 0. So I have 3 times, when I put in 0, I'm going to get a positive number. And when I put in 0 to the next factor, I'm getting a negative number, right? So all I'm doing is I'm using this factored form of the equation here. So let me actually make this a little bit bigger so I can highlight this. I'm using this, actually. Let me just highlight the factored form, because this is the derivative. It's just in factored form, is all. So that's what I'm using to find the sign. And that's usually the easiest way to evaluate the derivative. Is just, if you only care about the sign, then that's what you want to use. All right, so what is that telling me? Okay, I've got positive, positive, negative. So this is going to be less than 0, which means it's decreasing. So I could even draw on my number line a little arrow that is decreasing as you go from left to right. Right? It's just a line with a slope, a negative slope. All right, so it's decreasing for x between -2 and 2. All right, and then we have one more interval to look at, and that we're going to look at, and again, you can just pick a number, maybe pick 3. Again, all I care about is the sign. So I'm just going to take that factored form of the derivative, and if I put in a positive 3, then this factor is positive, and this factor is also positive. So it's greater than 0, so it's increasing again. So if I put that on my number line, then that indicates that in that interval, that x interval, that when x is greater than 2, it's increasing again. So I'm going to add that here. X is greater than 2, right? That's, I've got, actually, I should have left more room. Anyway, so it's increasing when either x is less than 2 or x is greater, when x is less than -2 or greater than +2. It's increasing, and it's decreasing on that interval in the middle. All right, so that's the first part. So now we know the intervals on which the function is increasing and decreasing. Now, the second one is asking us to use the second derivative to find the intervals on which the function is concave up or concave down. So now let's take a look at the second derivative. All right, f prime of x. Okay, let me scroll up so we can actually see it. Now this one you probably want to go up to the non-factored form of the derivative because we want to take the derivative of the derivative. So let's use this 3x squared minus 12. So if I take the derivative of that, I get 6x, and then derivative of -12 is 0. Okay. So now let's do this. Let's set this equal to 0, and that will tell us, where the function might be changing concavity, right? Because if it changes from positive to negative, it's got to pass through 0 if it's continuous, right? So if the derivative is continuous, which it is. So I'm going to set it equal to 0, and that gives us that x equals 0. Okay. Now you could call this a critical point, but oftentimes this is a candidate. It's not, since we already used the word critical point to define the points where the derivative is 0. We're going to call this something different, right? This is a candidate because now we're looking at the second derivative. It's a candidate for an inflection point, is what it is. So, let's evaluate the concavity of this function on either side of 0 to see if it actually does change concavity. And again, we've got the function here, so we can look at f double prime at something negative, like you say -1. You could pick a test point, or you could just kind of reason out that if x is negative, then the whole thing's going to be negative, right? Because it's just 6 times a negative number, and so it's going to be less than 0. So it has to be concave down, right? It has to be concave down when x is less than 0. And the second derivative at something bigger, so let's maybe pick 1, but it doesn't really matter. Any positive number, you take 6 times a positive number, it's got to be positive, right? So it's concave up, all right? So, so we're going to say that it's concave up for x greater than 0, and it's concave down for x less than 0. Okay. Now at 0, the derivative is 0, right? Because that's what we we figured it out. But so it doesn't really have, you can't say it's concave up or concave down at 0. So that's why I have greater than and less than instead of greater than or equal to or less than or equal to. Right? Now, if I was going to use interval notation, I would say, okay, x greater than 0, that's just 0, infinity, right? If I use interval notation, and it would be a curved bracket. And I believe that the online homework asks for interval notation. So you got to make sure you have the right brackets on there. You want a curved parenthesis. And x less than 0 would be minus infinity to 0, and you want parentheses on either side. All right. Okay. Well, that's all the examples I have for this section, and I'll see you in class.